Hi, I'm Andrew Turberfield from Oxford. I'm going to start with some thoughts on design, because that's what the workshop is normally about, and then go on to some accounts of our experiments and where they might be going. It's gone wrong a bit, but never mind. There's a sort of classic design, build, test cycle. And that is a rather more sophisticated and still erroneous system, which is what we're aiming for. And the idea is to do as much as possible in silico before you commit to experiment. And ideally, you'd spend all your time, or all your computer time, getting things right. Build once, test once, you've got it right, you don't even need to complete the circle. That's the ideal. So what does that in silico series of loops actually involve? I mean, there are basically two classes of components as far as I can see. You want knowledge-based design tools that make use of what you know. So empirical design rules, I mean, we already do this in origami. There are packages that tell you how to break and route your staples. Sequence optimization. You can go further. I mean, how do you assemble something? Annealing profiles for origami. What we find particularly difficult is assembling multiple components, so assistance with design of that. And clearly, there's a great hole in this, which is waiting to be filled by machine learning techniques. Simulation is part of this process. It isn't just what the thing looks like when you've made it. We're really interested in how you make it efficiently. So how do you assemble multi-component objects? Can you simulate the assembly process and use simulation to get that right, again, before you commit to making it? When you've made it, it's rarely a static structure you want. It's something with some sort of function. So can you investigate how it operates, simulate the function, simulate a molecular machine, again, get that right before you start to make it. And this is what you'd be trying to do. You'd be trying to improve your assembly yields, optimize its dynamic properties, whether it's a molecular computer, a signaling cascade, a molecular machine, improve structural stability if that's what you want. Control physical chemical environment, for example, to control chemical reactions, which is what I'm going to come on to. Okay, that was just inserted in response to a question this morning as, can you make these things move? So we're interested in atomically precise manufacture. It's not all we're interested in, but it's a major focus, which means building things, building block by building block, not atom by atom, at least not yet, but molecule by molecule. And I'm going to talk to you about two projects. This is the first. This is actually work done by Eric Benson here, who's going to talk more this afternoon, so I will skip a lot of the details. It's a part of a collaboration with William, funded by the DOE, and it was inspired by work by Eric Drexler. And what we've made is that, which is exactly what it looks like. It's inspired by a macroscopic two-dimensional printer. It's a device for positioning a write head over a DNA canvas and performing write operations at programmed positions. So it's a two-dimensional molecular printer. And this is a sort of baby first step towards Eric's vision of molecular assemblers that build things by positioning building blocks and sticking devices, structures, materials together in the limit atom by atom in a massively parallel way. I mean, you can think of 10 to the 12 of these machines all operating simultaneously. And it's a general purpose machine. I mean, you can program this to, in our case, modify the canvas in any pattern you choose, in any sequence that you choose. It's a machine that you program to perform a task. And I hope Eric will tell you a bit more about this, but what we've done with it is pattern add fluorophores, in fact, to the DNA canvas. We've written by catalyzing strand displacement reactions to add, to hybridize fluorescently labeled strands to a canvas. And what we need to do with our software design tools, or the ones that you're going to produce for us, is improve the assembly yield, and in particular, improve our success in sticking together the three origami components that make up that structure. Optimize its dynamic properties. How do you reposition the write head without it getting stuck? Improve the precision of writing. Do more than we do now in terms of picking and placing building blocks, do cleverer things, and in the limit extend it to three-dimensional printing. So this is a different project. This is what we call the synthetic ribosome project. The idea is to build a polymer now, building block by building block. So there is, in fact, less spatial control, except in the sense that you're putting these building blocks, concatenating them to make a one-dimensional primary sequence that in the limit you would hope might fold up to make a defined three-dimensional structure. This is what the ribosome does. Our system will never do it as well as the ribosome does, but it has the potential to work with completely non-biological building blocks, completely non-biological backbone units. And it exploits the principle of DNA templated chemistry developed by David Liu at Harvard, which is illustrated here. You have your organic chemistry, the clever stuff, conjugated to DNA adapters. You use the DNA adapters to lock the building blocks together. These things are present in solution at such a low concentration that reactions are effectively off, but this enforced localization turns the reactions on again. So this is the crudest form of catalysis, simply by co-localization. So here we have an initiator and a bifunctional building block. This is Wittig chemistry. That phosphonium ylide attacks that aldehyde. You get a transfer of that functional group. There's a new carbon-carbon double bond, which is a new backbone linkage. You get rid of that spent adapter, you bring in a new one, and you do it again. So you are, as in the ribosome, building up your polymer, building block by building block, in a programmed sequence. What we want to do, what we are trying to do, I'm not showing you details here, is create a genetically programmed system of molecular machinery. So rather than, as we did in those experiments, add strands one by one in a pipette-controlled sequence, we've got a soup of reactants, each reactant labeled with its own DNA adapter, and a molecular machine that reads a gene, which tells it which one to pluck out of solution and to add next. So you've got a genetically programmed polymer synthesis, which is what the ribosome does. And if you can do that, then you can create a library of genes. You can have 10 to the 12 machines making 10 to the 12 different products in parallel. And if you can do that, you can select, you can read back. If you keep the gene attached to the product, you can do a discovery experiment. You can even implement molecular evolution. So in the limit, this is a tool for molecular discovery. You can create and sample libraries that nobody has been able to create and sample before. And there, we need to optimize the operation of our molecular machinery. We need to improve the precision of co-localization, which means doing things we aren't doing at the moment, but engineering a reaction environment, engineering, if you like, a synthetic enzyme pocket, doing better job of controlling and activating chemistry by not just anchoring these reactants where they can knock into each other by random hazard, but by creating a pocket in which they sit and are positioned as in, this is a synthetic enzyme. So, ambition, where do we want to go? I'm not quite sure of the timescale for this, but it starts now. We want to put these projects together. So here's a challenge. There is a 3 by 3 by 3 array of building blocks. Say we've got a library of 10 components. Okay, there are 10 to the 27 possible ways of making that thing. We want to use our molecular assemblers, our positioning devices, spatially controlled chemistry, to control how we position things, put them together to create a chosen one, or a library of these three-dimensional structures. What do we need? We need the building blocks. We don't want to do DNA strand displacement anymore. We want to do proper chemistry. We want to build these things by proper reactions. Ambition number 2, we want to move beyond DNA. So that on the left is our implementation of that on our right, which was the sort of naive design drawing that we started with. But that on the left is a floppy, horrible thing that isn't very precise at all, in common with all DNA nanostructures. That on the right was conceived as beautifully rigid, totally under control. Actually, what we want to do is get more like that. And the ambition is to use these, second-rate, first-generation molecular printers to build those out of different materials. And again, the question is, what do we build them out of? What are our building blocks? Okay, thank you.
So this is really beautiful. You talked about 10 to the 12 different processes going on all at the same time. Do you run into issues with cross-reactivity and control of all of those kinds of things happening at once? I know you haven't realized the 10 to the 12, but do you see those issues coming up?
I mean, we do 10 to the 12 of the same thing simultaneously. 10 to the 12 is only a picomole. We can do more than that if we wanted to. Basically, no is the answer. I mean, what saves you, and the whole principle is that this is all very dilute. So everything that you want to occur is intramolecular within a complex. Everything you don't want to occur is intermolecular. So local concentrations we've enhanced to millimolar. Average concentrations are micromolar, nanomolar, picomolar. So when you test for cross reactions, you don't see them. That's an experimental answer. Lee, shout.
I'm not sure I'm allowed to shout. A crazy idea. Have you thought about immobilizing, placing these molecular printers inside some droplets where you might then have some selected ion transfer, molecular transfer through gates? So what you can do is play games at multiple levels. So you're not just playing a game with your sequence, but you can also play a game with the way these cargo carriers interact with each other in solution, and then are doing the printing inside, say, an artificial cell.
Are you talking about the 2D printers or the synthetic ribosome?
No, I'm talking about the 2D printers, first of all.
The answer is we're nowhere near that level yet.
Okay.
We've got a lot of optimization to do.
Okay, I have an idea. I don't think you need to optimize quite like you think, but anyway, it's very nice.